Hi everybody, welcome back. We're going to talk about the way that acids and bases actually work. And I'm sure there's lots of other videos and things you can go and look at. I'm going to do my best with what I've got here, but I'm going to try to link up some extra videos for you to really explore this, maybe an interactive even, but which is kind of the best way to learn about it. But water in general should be not really thought of as just these, a lot of the time you'll see water drawn like this, H2O, right? So we have H2O. And it's often drawn just as these little tiny molecules that are sort of floating around. Blah, copy, I'm just going to make a bunch of them. Oops, I should paste them as paste and paste and paste. Okay, so sometimes they're drawn this way, and they're kind of shown as floating around and bouncing around. But what we really want to do when we think about water is we want to kind of actually arrange it more like it was a web, where the hydrogens and the oxygens are kind of looking towards one another. And it gets even more interesting is that it's not exactly clear where one water begins and one water ends. And one oxygen and one hydrogen might be connected to, four or five. One oxygen might be connected to four, maybe five oxygens all at the same time, all really close together and sort of spreading out. And this is called a network of hydrogen bonds. Now, this is neutral water. Neutral water has all these water molecules just hanging around in a big old web. But when you introduce one of these acids, copy and paste, when you introduce an acid or a base, what you're doing is you're going to be adding an H plus in there. The thing about this H plus is it's got a much stronger, we're adding this extra H plus, and we got to find a place for it. And what that's really going to be doing is it's going to disrupt the whole network. So if I put this H plus right here, for example, suddenly a new sort of bond forms between this oxygen. And this oxygen now has three hydrogens, and it doesn't want to share anymore. And so these disappear, and the network kind of closes up a little bit, or it changes. And that change in the network has a lot of different effects all throughout. Now this network has a positive charge on it. It's all different. So for chemically, this is suddenly a different system. We can do the same trick by I'm going to just have to make a little bit more space here. So if we do the same trick over here, and we add an OH, maybe I'll draw the OH in purple. The OH is going to be sort of negatively charged, and it's going to grab onto one of these hydrogens, and it also doesn't want to play nice. So all of a sudden it breaks that little bond, and that makes the network different. The network's not the same. Now this network is not quite the same. It wants to grab a hydrogen, so it kind of causes a little bit of a difference in the network. The network is not as balanced as it was before, and that loss of balance changes the way it behaves to other chemicals. So the water molecules continuously split up into hydrogen and hydroxide ions. This is known as equilibrium. So that's another thing that's happening here that I didn't talk about, is that when we're back in this side, when it's an equal system, then the hydrogens and the oxygens can sort of change partners. As they change partners, they might become H+, they might become OH, they might go back and forth and back and forth, and they're in a state of what's called dynamic equilibrium, which we'll talk about a lot more in Chemistry 4DS, talking about it right now. And so that's the idea that this water can break apart and form back together into H plus and OH ions. Or, depending on who you talk to, they might actually describe it as a reaction between two water molecules, H2O plus H2O, and say that two water molecules can change partners and form H3O plus and OH minus. And in both cases, the system stayed neutral. It's just that this is more true because look at how the hydrogen incorporated here. See, the hydrogen doesn't actually float around by itself. It tries to find a partner. So that's a better way of representing it. This is the hydroxide. This one is called hydroxide. And this one is called hydronium. And this is the most correct way to talk about acids and bases is as hydronium and hydroxide. Older texts will refer to the proton instead. But hydronium is what you'll actually find if you could study the system at the microscopic level. If you could shrink down, you would find these H3Os with a positive charge, these hydronium ions. Acids and bases are chemicals that when dissolved in water change this equilibrium by adding extra hydrogens or extra hydroxides. And these extra hydrogens go on to create extra hydroniums. So now that we know this, we're going to creating extra hydroniums. Too much of either ion can create a dangerous situation. This is a basic or an acidic solution. Your body's chemistry depends on there not being an imbalance in the water. Well, to a certain point. If you get if your body's water supply is pushed beyond the certain range of water molecules, so that there is too much hydronium or too much hydroxide, you essentially die. That's acidification of your blood. It's a really rare condition, but it is a very dangerous one. The amount of hydrogen ions is measured on a scale. So this hydrogen ions or hydronium, they're equal in number, is measured on a pH scale. pH stands for pourvoir d'hydrogène, which is power of hydrogen or hydrogen power scale. Hydrogen power. And that is because it is a base 10 system. So I don't know if you're very familiar with this, but essentially it's going to be this system, this scale, which runs from 1 to 14, is referring to a 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. So it is a scale that goes from 10 to the power of 1 all the way to 10 to the power of 14. And so, which we call pH 1 to 14. And so that's where it comes from, is the power symbols here. It's negative 14? No, it's possible. It's negative, yeah. It's negative. I had to double check myself there. It is negative 14. But anyways, so if the amount of hydrogen ions is equal to the amount of hydroxide ions, then we say it is neutral, and neutral is pH 7. So pure water is a pH 7. It has a power of 7 number of hydrogens and a power of 7 number of hydroxides. Power of 7 hydroniums to power of 7 hydroxides. This is all stuff we will cover in a later course, but we have a power of 7 number of H plus, and take all of this, copy and paste, of OH. So that's why it's equal, so it's neutral. So it's 7. Now that means that any other number is not equal. So any other number, because the power of hydrogen, equals 7. Or I'm not sure exactly what I was trying to say here. Maybe I'll just leave it. 7. Okay. So the 7 is the exponent there. So this is all extra. You don't really need to know this. You just need to know that pH 7 is neutral. It means that there's an equal amount of hydrogen and hydroxide. So it's equally balanced. When the acid is above pH, when acid is added, the pH will drop because you're going to be adding on that H plus side. So we've kind of got a teeter-totter here. You have an H plus and you have OH minus. If you add acid, you're pushing down on this number and you're going to be drifting towards 1, and this is 7 where it's equal. So you are going to push it towards 1, and so the number will go down. The more you push down on this hydrogen side, right, acid side, and then if you add base, you're going to be pushing down on the hydroxide side, so you'll push towards 14. And one of the tricks about acids and bases is that you can go back and forth as much as you like, and the system can be rebalanced in different ways. So when acid is added, the pH will drop below 7. When base is added, the pH will increase above 7. The scale goes from 1 to 14. There are some extreme examples that break this rule, but for the most part, 1 to 14 will explain almost everything you'll ever encounter in your lives. pH is measured with a pH meter, and we can determine the pH of a substance and classify it as either an acid or a base. Chemical indicators can be used to identify whether a substance is an acid or base. Chemical indicators such as litmus and phenolphthalein, which I had to memorize how to spell at one point, how as ridiculous as you can imagine, appear as one color when mixed with an acid. They become different colors when mixed with a base. So for example, phenolphthalein is a substance that is colorless when it's in an acid. When the pH is less than 7, and it becomes pink when the pH is higher than about 8. So when it's 8 or higher. So in that way, you can test for a basic sample by dropping a drop of phenolphthalein in, and if it turns pink, you know that it's basic. If anybody's ever worked at a pool or have ever owned a pool, you'll know that this is something you do pretty regularly, is you take a sample of pool water and you add a couple drops of indicator to it. And they usually have a couple of different things that you add, and you're looking for a certain combination of color to appear. And that color can tell you whether the water is safe for people or not safe for people. Blue litmus paper stays blue in a base, blue, and it turns red in an acid. And red litmus paper stays red and turns blue. So with litmus, it's easy to remember because it's blue for base and red for acid. So blue, always remember the B part. Blue equals base for litmus. All right. So I think we will talk about the scale itself on our next video. So hopefully you had fun today, and we will talk to you soon.